Hey Chemistry, today we are going to talk about the ideal gas law. So in the last section we learned that Avogadro noted the importance of being able to calculate the number of moles of a gas present under a given set of conditions. And so the laws of Avogadro, Boyle, Charles, and Gay-Lussac can be combined into a single mathematical statement that describes the relationship among pressure, volume, temperature, and the number of moles in the gas. The formula is called the ideal gas law because it works best when applied to problems involving gases contained under certain conditions. We know with science we always want these beautiful conditions that never seem to actually exist. The number of moles is the fourth variable that can be added to pressure, volume, and temperature as a way to describe a gas sample. Recall that as the other gas laws were presented, care was taken to state that the relationships hold true for fixed mass or given amount. Changing the number of particles present will affect at least one of the other variables. As a picture in your book on page 434 illustrates, increasing the number of particles present will raise the pressure. Think about putting air into a tire. If the volume and temperature are kept constant. If the pressure and temperature are constant, more gas particles are added, then the volume is going to increase. Think like more of a balloon, at least briefly. Because pressure, volume, and temperature and the number of moles are all interrelated, it would be helpful if one equation. And so page 434 gives you kind of a mathematical way of finding this equation, but ultimately what it comes down to is the ideal gas law is PV equals nRT. P equals pressure, V equals volume, N equals number of moles, T equals temperature, and R is a constant that was mathematically determined. Now, the key thing to note about R is your R is going to be different depending on what pressure unit you're using. So the three different R's can be found on page 435, okay? If you're using atmospheres, then your R is going to equal 0.0821. If you're using kilopascals, then your R is going to equal 8.314. And if you're using mmHg, then your R is going to equal 62.4. Now, it's important that all the other units stay the same. So your volume is always going to be in liters, your temperature is always going to be in Kelvin, and your number of moles is always going to be in moles. Alright, the R value you will probably use most is the ATM because that's the pressure unit that we use the most. Use the R in all problems where it's going to be atmospheres. Yeah, but again, making sure the temperature is in kelvins. Real versus ideal gas. What does the term ideal gas mean? An ideal gas is one whose particles take up no space and have no intermolecular attractive forces. An ideal gas follows the gas laws under all conditions. In the real world, no gas is truly ideal. All gas particles have some volume, however small it may be, because of the size of their atoms and the length of their bonds. All gas particles are subject to intermolecular interactions. So when is the ideal gas law not going to work? Real gases deviate most at extremely high pressures or extremely low temperatures. As the amount of space between particles and the speed with they move decrease, the effects on the volume is going to be important based on the intermolecular forces. And so real gases this gas law isn't going to work for things at extremely high or extremely low temperatures. And then the nature of particles making up a gas is also going to affect how ideally it behaves. The polar gas molecules, such as water vapor, generally have larger attractive forces, and so those forces are going to be changing things. But ultimately speaking, for everything in this chapter, you're going to be able to use the ideal gas law. So let's talk about how. Let's go through an example problem if we were given, if we're trying to use moles, okay? So calculate the number of moles of gas contained in a 3-liter vessel at 300 degrees Kelvin with a pressure of 1.5 atm. Alright, so let's write down what we know. The problem says a 3-liter vessel. So we know our volume equals 3 liters. Our temperature equals 300 Kelvin. They already converted it for us. Thank you, problem. Our pressure is 1.5 atm. And since we're using ATMs, we know that our R is going to be equal to 0.0821. So we've plugged all of these things in, and we want to know the N. So let's plug it in. We've got pressure equals 1.5 times volume is 3 equals N times R is 0.0821 times T is 300. Let's simplify. 1.5 times 3 equals 4.5. 0.821. Let's calculate this out. 0.0821 times 300 equals 24.63. This is multiplied over here, so we can divide by 24.63. So we have 4.5 divided by, and we end up with 0.18 moles equals N. And we know that it's already in moles because that is how the problem is solved. All right, so can you see that? There we go. Okay, so pretty simple. You just plug things in, right? And if you're given different variables, you plug in those variables. The one thing you need to remember is your R constant is going to be dependent on what pressure units you have. Now, let's change up a couple things. So recall from chapter 2 that density is mass per volume. And so if you don't have, if you're given density or you're given something else and asked to solve things, I'm going to get this work, you can rearrange your equation and you can change some things for mass divided by volume and things like that. So you could rearrange the entire equation to solve for the density of a gas. You could do density, because remember density is mass over volume. So if you're using number of moles to figure out molar mass, then you could do density equals mass times pressure divided by R constant times temperature. So that's another way. It's the same equation. We just plugged some different things in. Gosh, that glare is terrible. There we go. Okay, why might you need to know the density? Well, think about ways to fight a fire. One way to put out a fire is to remove its oxygen. So you'd cover it with another gas. And so what is our ideal gas law going to be using molar mass? Okay, so let's see if you're given certain things. Now the handy thing about this is you don't usually have to be converting too much as far as grams and moles and things like that. The units of the ideal gas law are already given to you. Okay, so what is the molar mass of a pure gas that has a density of 1.4 grams per liter at standard temperature and pressure? STP. Do we remember what the value of STP is? Let's see. So the problem said that pure gas has a density of 1.4 grams per liter. Okay, so density equals 1.4 grams per liter. Then we've got standard temperature equals 0 degrees Celsius. Let's convert that. Plus 273 equals 273 degrees Kelvin. We don't like degrees with Kelvin. Standard temperature and standard pressure is 1 atm. Since we're using atms, that means our R value is going to be 0.0821. And we are solving for molar mass. Oh, that glare. There we go. Alright, so this is what was given to us in the problem. So we converted our temperature to pressure, and now we can calculate to solve. Alright, so let's plug it in. So we've got density equals mass over mass times pressure over R times temperature. So let's plug it in. We've got 1.4 equals mass times pressure is 1 divided by 0.0821 times temperature, which is 273. Now we just start to simplify that. So 1.4 equals, we can get rid of the 1 because 1 times m is n. And then calculate 0.0821 times 273 is going to be 22.41. So to get rid of this, since we're dividing, we multiply by 22.41 on both sides. 4, 4. And we end up with 31.37 grams per mole is going to be our molar mass. All right. So again, we're just plugging things in. Okay. So this is your equation rewritten for density. This is your initial ideal gas law. All you do is figure out what you have. You write down those variables. You plug it in, and you go. Okay. So your Juno pod includes 2 sets of problems. The first set of problems is the one using moles, using the n number of moles, and then your second one is going to be using density. Okay. Now remember, okay, your mass divided by molar mass, things like that. So for most of this, the problem is going to give you things. You don't really need to be converting too much. Just make sure that all your units are in the correct thing. Remember to convert all of your temperatures to Kelvin. And remember that your R constant is going to change if your units change. Okay? But other than that, you guys, it's just an algebraic equation. Okay? So you got this. Good luck. And I'll talk to you guys soon. Bye.